Last time we looked at some properties of Hermitian matrices in general. This time we are going to look specifically at some matrices associated with graphs, and these are going to be real symmetric matrices. So let me share screen. Okay, so today we are going to look at Laplacian matrices associated with graphs, and I'll go on to define these. Let's start with adjacency matrices. So G is going to denote an undirected graph. It has vertex set V and edge set E, and the number of vertices is given by n. The adjacency matrix of this graph, which we'll denote by A, and we'll subscript it by G if we want to make it clear which graph we are referring to. So if there are n vertices, then this is a square matrix, an n by n matrix. And its element, the ijth element, is 1 if there's an edge between vertex I and vertex j, and it's 0 otherwise. Okay, so it's an n by n matrix whose rows and columns you can think of as being indexed by the vertices of the graph. A is symmetric since the graph is undirected. So if there's an edge between I and j, there's also an edge between j and I. The powers of this matrix count paths in the graph. So let's see why that is so. What's the xyth element of the kth power of the adjacency matrix? By the matrix multiplication formula, it's the sum. It's the sum of A V0 V1, A V1 V2, A Vk minus 1 Vk, where the sum is taken over all possible intermediate indices V1, V2, Vk minus 1, but V0 is fixed to be x and Vk is fixed to be y. Okay, that's the xyth element. Okay, so what's the sum again? So these A's are take values either 0 or 1. So the product is 1 if all of them are 1, and it's 0 otherwise. So the only terms that contribute, so for this term to be, for the product to be 1, you need there to be an edge between V0, which is x, and V1, an edge between V1 and V2, and similarly an edge between Vk minus 1 and Vk, which is y. In other words, there's a path from x to y. Okay, so this is one such path, one choice of V1, V2 through Vk minus 1, which gives us a path from x to y. And then we count 1 for each such path and we add up. So we are counting the total number of k-step paths from x to y, where the 1 here indicates is the indicator of an event. So by this we mean it takes the value 1 if this event occurs and it's 0 otherwise. I should also clarify that when we are talking about paths here, we don't restrict to simple paths. So vertices are allowed to be repeated. V1 may be the same as V5 along this path. So there may be loops on the path. Okay, so we are not only counting simple paths, but also paths which include loops. And then a to the k counts all such k-step paths. Okay, that's all about adjacency matrices. So let's move on to defining the Laplacian. Let's denote by D the n by n diagonal matrix whose diagonal element, the V diagonal element, is the degree of the vertex V. Okay, so let's look again at the adjacency matrix. It had a 1 from V to W. So AVW was 1 if VW was an edge. So there was a 1 for each edge incident on the vertex V. So if you look at the Vth row sum of this matrix, how many ones are there? There's a 1 for every edge. So there are degree V many ones along this matrix. So if you look at the row sum, you get the degree of V. Okay. So D is the diagonal matrix whose diagonal elements are the same as the row sums of the matrix. They are the degree of V. And the Laplacian is defined as D minus A. So you take the degrees along the diagonals, and in the off diagonal, you put a -1 if there's an edge. A was a symmetric matrix. We saw that already. D is diagonal, so it's symmetric, and hence L is symmetric as well. And we also saw that the row sums of A are D, so the row sums of D minus A are 0. The row sums of the Laplacian are 0. Okay, so now if we look at minus L, L has positive entries on the diagonal, negative off the diagonal, and minus L is the other way around. So it has non-negative off diagonal elements, and its row sums are 0 as well. And we recognize what a matrix of this form is. It's the generator matrix of some Markov process on the state space, which is here the vertex set V. Okay, so what Markov process is this the generator for? So take a moment to think about it. See if you can answer that question for yourself. Okay, so minus L is the generator for the continuous time random walk on V, also known as the Markov jump process, with jump rate 1 along each edge. Why is that? So the off diagonal, so the ijth element of minus L is 1, is the same as the ijth element of minus A, so of A. So it's 1 if there's an edge between I and j, and 0 otherwise. So what it's saying is that the Markov process has rate 1 of moving from I to j if there's an edge between I and j, and rate 0 of moving from I to j otherwise. So that's just this continuous time random walk with jump rate 1 along each edge. Okay, and this is the random walk we are going to study later on, and that's the motivation for us introducing Laplacian matrices. Okay, there are a few remarks before we go on to study properties of the Laplacian in more detail. I've defined the Laplacian as this matrix D minus A. The term Laplacian is also used for some other closely related matrices. So I'll mention these other definitions because you might come across them in reading a textbook or a paper. So another matrix for which the term is used is a scaled version of our Laplacian. So this is instead of D minus A, we've multiplied on the left and the right by D to the minus half. And then it gives us this rescaled matrix. And this is called the combinatorial or normalized Laplacian to distinguish it from what we defined, which is also called the algebraic Laplacian. So we also defined a random walk on V associated with whose generator is minus the Laplacian, and that was the walk which had rate 1 along every edge. So if you think of what it does, if you construct it in terms of clocks at the vertices, then the time it spends at some vertex is exponential with parameter equal to the degree of the vertex. So at high degree vertices, it spends less time because there are lots of other edges it can walk along. And the mean time it spends is 1 over the degree, and then it jumps to a neighboring vertex. Instead, you could have defined a random walk. It's quite natural to define it as spending unit time on average at each vertex, so exponential 1 random time at each vertex, and then it jumps uniformly at random to a neighboring vertex. So that's another different random walk you can define on the graph. And this random walk has generator the identity minus T inverse A. And this matrix is sometimes called the random walk Laplacian. Okay, so there are, this is just to warn you that there are some other closely related matrices which are also called Laplacians, but the one we'll use is T minus A. You may have come across Laplacians in another context in studying differential equations. If you looked at the heat equation in physics, then that has that's governed by a differential operator of this form on Rn. So it's the sum of the second partial derivatives. And this is called the Laplace operator. So what's the connection of this operator with the Laplacian matrix of a graph? Okay, so if you looked at this Laplace operator and you looked at minus delta, that's in fact the generator of a Markov process, a very famous Markov process, namely Brownian motion. Okay, that's quite different from Markov processes we study in this course. It has a continuous state space. We only study discrete and even finite state spaces here, but it's also Markovian. Well, it's a very famous process in its own right. And the minus the Laplacian operator is the generator of this Markov process. Now, if we discretized Rn, n-dimensional Euclidean space, with the integer lattice and then multiplied it by epsilon to make the mesh finer, we are going, if epsilon is small, then we are placing a fine mesh on Rn. And if you consider the simple symmetric random walk on this lattice, so from any vertex, you move equally, you're equally likely to move to each of the neighbors. And then you let epsilon go to 0 and rescale time appropriately. Then this random walk converges to Brownian motion, and the graph Laplacian on this integer lattice, rescaled integer lattice, converges to this Laplace operator. So that's somehow the origin of the name Laplacian for this matrix. It was by analogy with the Laplace operator here, and it generalizes the study of random walks from the integer lattice to arbitrary graphs. Okay, so that was a bit about how the name came about. Now we are going to go on to study some properties of this matrix we have defined. For us in this course, the motivation will mainly come from the continuous time random walk, but I should mention that there's a whole area of graph theory focused on studying eigenvalues and eigenvectors of the Laplacian because they provide a lot of information about the graph. And so this branch of graph theory is called spectral graph theory. We aren't going to go into this. We are just going to see one very simple example here, which relates the eigenvalues of the Laplacian to the connectivity of the graph. Okay, so with that by way of motivation, let's ask what can we say about the eigenvalues of the Laplacian. Okay, so I want to tell you that you already know one eigenvector and one eigenvalue of the Laplacian immediately from its definition. And Okay, before telling you about that, let me remind you of some notation. We'll use boldface 0 and boldface 1 to denote the all 0 and all 1 vectors. Also, vectors will be column vectors unless specified otherwise. Okay, we notice that all the row sums of L are the same and in fact equal to 0 because it's D minus A, and D was by definition the same as the row sum of A. Okay, if all the row sums are the same, then the all 1 vector is an eigenvector of L, because if you multiply L, the matrix L, by the column vector of all 1s, what you are doing is you are calculating the row sums. And so you get, in this case, the row sums are 0, so you get the all 0 vector, which is 0 times the all 1 vector. Okay, so the matrix multiplying this vector is just a scalar multiplying this vector. So this vector is an eigenvector, and the scalar here is the eigenvalue. So the eigenvalue is 0, and all 1 vector is an eigenvector. Okay, so we've found one eigenvector and one eigenvalue of L pretty much effortlessly. But can we say a bit more about the other eigenvalues? And we can. So we'll go on to do that. And we are going to do so by looking at quadratic forms on the Laplacian and using the Rayleigh-Ritz theorem, which we studied last time. And if you've forgotten it, now's a good time to remind yourself of the Rayleigh-Ritz theorem. Okay, so let X be any arbitrary column vector in Rn. Then X transpose Lx, so we'll call this kind of object a quadratic form. So it's a quadratic in X, and okay, L defines this quadratic. And our claim is that if you calculate this, so L is a matrix, X is a column vector, Lx is a column vector, and X transpose times that is a scalar. So this whole thing is a scalar. And our claim is that this can be expressed as the sum over all edges in the graph of xi minus xj squared. Right? So you should think of X as being indexed by the vertices of the graph. And then this quadratic form is the sum of the squared differences along the edges of the graph. Okay, and since it's a sum of squares, it is necessarily non-negative. Is the statement of the claim clear? Okay, if so, let's go on to prove it. The proof is just a bit of straightforward calculation. So let's start with the right-hand side and expand it out. So I've rewritten the sum over edges as the sum over pairs of vertices ij, such that there's an edge between I and j. And I've written the exact same thing here. So where did this half come from? This is just notation. When I write the sum over ij in E, what I mean is that I count each edge once in this sum. When I write it this way, when I say count pairs of vertices such that they form an edge, then I'm counting each edge twice, once as ij and once as ji. Okay, and that's why I have this half here. And then I've just expanded out the square. And now let's expand out each term in the sum. Now, by symmetry, the graph is undirected, so the sum of xi squared over all such vertex pairs, ordered pairs of vertices such that there's an edge, is the same as the sum of xj squared. So I'll get rid of the half and keep just one of the sums. So I've written the sum of xi squared. This is a double sum over indices, and I've just written that out in full. So we can first sum over I in the vertex set, and then sum over j such that there's an edge between I and j of xi squared. And then I have the minus 2 xi xj term, so the 2 cancels the half, and I've again written out this double sum as a sum over I, and then an inner sum over j such that there's an edge between I and j of xi xj. Okay, so now let's look at this sum here of xi squared over j. Xi squared doesn't depend on j, so it's the same term summed over each j in the vertex set such that ij is an edge. So we are summing a constant how many times? The number of times for which there's an edge from I to some j. That's just the degree of I. Okay, so this inner sum becomes xi squared times the degree of I. And then the outer sum is sum over I and v. And then, okay, I'm rewriting this sum here as a double sum over all pairs of vertices, aij times xi xj. And why are these two things the same? Aij is 1 only if there's an edge here. So it precisely counts those terms for which there's an edge between I and j. And if there's no edge, the adjacency matrix has a 0 element there. That was the definition of the adjacency matrix. Okay, and so this first sum, the sum over degree I times xi squared is just x transpose dx. You can check that for yourself. And this, by the matrix multiplication formula, is just x transpose ax. And then by definition, that's x transpose nx, which is the left-hand side. Okay, so that's just matrix algebra. Okay, so we've shown that this that for any x in Rn, this quadratic form x transpose Lx has this representation as the sum over edges of xi minus xj squared. And because it's sum of squares, it's non-negative. And we can use that calculation to say something about the eigenvalues. So first observe that L is a real symmetric matrix, so it's a Hermitian matrix, and so its eigenvalues are real. And because they are real, they can be ordered. We can compare two eigenvalues and say this one is bigger than that one. And so we can order them in increasing order. And then the Rayleigh-Ritz theorem tells us that the smallest eigenvalue is the minimum over all non-zero vectors of this ratio, which we call the Rayleigh quotient. So the numerator is this quadratic form x transpose Lx, and the denominator is just x transpose x, which is the squared norm of the vector x. Okay, we can also rewrite this ratio as follows. So notice the following. X is a non-zero vector. If I take some multiple of this vector, some scalar multiple of this vector, c times this vector, and calculate this, then the numerator gets multiplied by c squared. Similarly, if I multiply by c here, the denominator also gets multiplied by c squared, so they cancel. So this ratio is the same for a vector as for any multiple of that vector, right? So the ratio stays constant along a ray. So we can simply take that particular constant c, which normalizes this vector to have unit length, and that doesn't change this ratio. So instead of taking the minimum over all non-zero vectors, we can reduce it to a minimum over all vectors of length 1. And then we just have x transpose Lx because the denominator becomes 1. In that case, it's the squared norm, the squared length is 1. Okay, so we can rewrite lambda 1, the smallest eigenvalue, as the minimum of this quadratic form over all vectors of length 1. Okay, and we showed that this quadratic form is always non-negative, which means the minimum is also non-negative. And so lambda 1 is non-negative. But in fact, we actually found one of the eigenvalues. We didn't know yet which one of these it was, but we found that 0 is an eigenvalue corresponding to the all one vector. Right? So we know 0 is an eigenvalue. And since all eigenvalues are non-negative, this must be the smallest eigenvalue. So lambda 1 is 0. And all these others are non-negative. Can we say more? Okay, before we come to that, I just wanted to remind you of some terminology. If we have a Hermitian matrix L, not necessarily a Laplacian, any Hermitian matrix L, for which X transpose Lx, or for complex vectors X Hermitian Lx, if this quadratic form is non-negative for every X, such a matrix is called positive semi-definite. You've almost certainly come across this term before. So I'm just reminding you that a Hermitian matrix for which X transpose Lx is always non-negative is called a positive semi-definite matrix. So what we have proved here is that the eigenvalues of a positive semi-definite matrix are non-negative. That's an immediate implication of the Rayleigh-Ritz theorem. Okay, so we have proved in particular that the Laplacian matrix is positive semi-definite. Can we say more? Is it positive definite, meaning is this quadratic form strictly positive for all non-zero x, for all x such that norm x equals 1? No, sorry, this can't be positive definite because it has an eigenvalue of 0. So, okay, so we are not asking if it's positive definite, we are asking, can we say that all other eigenvalues are strictly positive? That's the next question we are going to ask. So is lambda 2 strictly positive? Okay, so let's use the Rayleigh-Ritz theorem again. So what was lambda 2 by the Rayleigh-Ritz theorem? It's the minimum over all x, which are orthogonal to the eigenvector corresponding to lambda 1. That was the all one vector. So we want to minimize over all x orthogonal to 1 the Rayleigh quotient x transpose Lx over x transpose x. But we saw that by restricting to length 1 vectors, we can drop the denominator. So we want to minimize x transpose Lx over all length 1 vectors orthogonal to the all one vector. And we saw already that x transpose Lx can be represented in this way as the sum of squared differences along edges. Okay, now what does it mean for a vector x to be orthogonal to the all one vector? What kinds of vectors can be orthogonal? So it's easy to see that if x is orthogonal to 1, then it cannot be a constant vector. For it to be orthogonal, the inner product has to be 0. If x is some constant non-zero vector, 0 never counts as an eigenvector. Anyway, its length is not 1. So if x is some other constant c, then it's c times the all one vector. X transpose x is just c times 1 transpose 1, which becomes n. So it's c times n, it's not 0. So it has to be a non-constant vector if it's orthogonal to 1. Okay, now if x is not a constant vector, and if the graph G is connected, then I claim there's at least one edge along which xi is not the same as xj, so that at the endpoints of this edge, the values are different. So let's think about why that is true. X is not a constant vector, so there is some vertex u and some vertex v such that xu is different from xv. Okay, and the graph is connected, so there's a path between u and v. Now maybe xu is the same as x at the next vertex along the path and the same as the next vertex and so on, but it can't be the same forever because by the time you get to v, it has to have a different value. The value is different at v than at u. So there must be some step on this path at which the value changed. So there's some edge ij along this path such that xi is not the same as xj. And you can also see why it's necessary that G be connected in order for me to be able to say this. Because if G were disconnected, if it, say, consisted of two connected components which were disjoint from each other, then X could take a constant value on this piece, a different constant value on this piece. So it's not constant on the whole graph, but along every edge, the values are the same. Okay, because there's no edge between these two pieces, so there's no edge on which the values differ. Okay, so if the graph is connected and X is a non-constant vector, then there must be some edge along which these values differ. And then the square of xi minus xj on that edge is strictly positive. All other terms in the sum are non-negative. So the sum as a whole is strictly positive. And so this quantity here is positive and lambda 2 is positive. Okay. Okay, so on a connected graph, we've shown that this sum is strictly positive for any non-constant vector. And therefore, lambda 2 is strictly positive. Okay, for those of you who maybe feel I have glossed over taking the minimum step, I should explain that if we take, there's some x vector x at which this minimum is attained. So look at that particular vector x where the minimum is attained. It's orthogonal to the all one vector, so it's not constant. And at that minimizer, the sum is strictly positive if the graph is connected. And so this eigenvalue lambda 2 is strictly positive. Okay, so if the graph is connected, it's positive. What happens if the graph is disconnected? Is lambda 2 still positive, or can lambda 2 be 0? And in fact, how many times is the eigenvalue of 0 repeated on an arbitrary graph? So the answer to that question is given by this theorem, which says that for a graph G with k connected components, the Laplacian of G, the eigenvalue 0 of the Laplacian is repeated k times, and all other eigenvalues are strictly positive. Okay, so that's the theorem. So make sure you understand the statement of the theorem. Okay, and the theorem is going to follow easily from this lemma. And the lemma is the following. So suppose G is the disjoint union of these k graphs, G1 through Gk, meaning that the vertex, these have disjoint vertex sets, and so the vertex set is the disjoint union of these vertex sets, and similarly for the edge set. Okay, then the spectrum of G, by spectrum I mean the set of all the eigenvalues of G. And you should now think of this as a multiset. So a multiset is in a set, if an element is repeated, you don't care. You only count it once, but in a multiset, you keep track of the multiplicity of elements. So we can think of the spectrum of G as a multiset. Repeated eigenvalues are written as many times as they are repeated. Then the lemma says that the spectrum of G is the union of the spectra of G1, G2 through Gk And this notation union with a plus sign within it says we should take the union as multiset. So we should keep track of the multiplicity. So here's an example. If A is this multiset and B is this multiset, then the multiset union counts 1 twice because it comes once from A and once from B. Okay, I hope the notation is clear and the statement of the lemma is clear. Now, if you accept this lemma, why does the theorem follow? We proved for a connected graph that it has one eigenvalue of 0 and all other eigenvalues are strictly positive. Lambda 2 is strictly positive and lambda 2 was the second smallest, so all the others are also strictly positive. So if G1 is connected, it has one eigenvalue of 0. Similarly for G2 through Gk. So if a graph has k connected components, G1 through Gk, it can be expressed as the disjoint union of these connected components. Each one has one eigenvalue of 0 and the remaining strictly positive eigenvalues. And so G has k eigenvalues of 0 and all the others strictly positive. And that's the proof of the theorem. Okay, is that clear? Good. So if we take the lemma for granted, the proof of the theorem is easy. So all we have left to do is to prove this lemma. Okay, so let's prove the lemma. So if G is the disjoint union of these graphs, then let's number the vertices so that the vertices of G1 are written first, then the vertices of G2, and so on. And if we do that, it's easy to see that the Laplacian of G has this block diagonal structure. So there are only edges within G1, so there are no edges between vertices of G1 and vertices of G2. So everything here, the diagonals are the degrees, and everything off diagonal comes from the adjacency matrix. There are no edges here, so the elements of the adjacency matrix here are 0, and similarly everywhere off the diagonal block, they are 0. And within these diagonal blocks, they are given by the corresponding subgraph G1, G2 through Gk. Okay, so the Laplacian matrix has this block diagonal structure. And we also know a lot about each of these Laplacians because we've just been studying them. So this is a Hermitian matrix. It has a basis of eigenvectors, an orthonormal basis of eigenvectors, in fact. So we also saw that for a graph, the all one vector is an eigenvector with eigenvalue 0. So that's true for each of these subgraphs. And in addition, they have a basis of eigenvectors. So now let Vi be an eigenvector of the Laplacian of the component Gi with eigenvalue lambda I. I want to claim that from this eigenvector, I can construct an eigenvector of the big Laplacian Lg with exactly the same eigenvalue. And how do I do that? So I write the column vector Vi corresponding to the ith block here, and I pad it out with zeros above and zeros below. Now, if I multiply this matrix Lg by that column vector Vi padded with zeros above and below, what do we get? The matrix multiplication becomes a block by block multiplication. So Lg1 multiplies zeros, becomes 0. Similarly, the second block becomes 0, and so on for everything except the ith block. The ith block is Lgi Vi, which gives us lambda I Vi, and then we have zeros below as well. So we get lambda I times this long column vector with vi in the ith block and zeros everywhere else. Okay, and that's what I've said here. So we can take this eigenvector vi of the of the block LGI, and we can construct an eigenvector of LG by stacking zeros above and below vi. And so for every eigenvalue lambda I of LGI, we have an eigenvalue lambda I of LG with the modified eigenvector. Okay. So what we've shown is that every eigenvalue of every subblock gets counted once as an eigenvalue of G. Okay, to show that, I should show that vectors vi and vj corresponding to different subblocks are not linearly dependent, but that's straightforward. They are non-zero at different positions, and so they are in fact, we started with orthonormal vectors, and by padding zeros elsewhere, they remain orthonormal. Okay. Okay, so for every eigenvector of LG, we've extended it to an eigenvector of LG with the same eigenvalue. And so the spectrum of G contains each of these spectra with the appropriate multiplicities as multisets. And the lemma claim they are equal, and to show they are equal, it's just a matter of counting. So if Gi has ni vertices, then the total number of vertices is the sum of the ni. LGI has ni eigenvectors, and we have padded them out. So it contributed ni eigenvectors to G. And so we already obtained n orthonormal eigenvectors of LG. And LG is an n by n matrix, so it can only have n eigenvalues and n eigenvectors. So we found all of them. Okay, and that completes the proof of the lemma. Okay, so that's all I wanted to say about Laplacians of graphs. There are some examples in the notes just for concreteness. I haven't made it clear how you calculate eigenvalues there, and so I don't expect you to know how to calculate them. But you can check that what's given in the notes are eigenvalues and eigenvectors. And the main thing to note is that the all-one vector is always an eigenvector with eigenvalue 0, and all other eigenvectors are non-negative. In fact, they are strictly positive if the graph is connected. And we've proved that the number of 0 eigenvalues of a Laplacian is exactly the number of connected components. So that's one thing the eigenvalues of the Laplacian tell us about the graph. They tell us how many connected components it has. They tell us more things, but those other things we will not study in this course. Okay, so I'll stop sharing now, and that's all for this lecture. And next time we are going to start studying the random walks on graphs for which the Laplacians or minus the Laplacians are the generators.